Okay, so in this chapter, we'll talk about fixed axis rotation. All right, now since I'm recording, I have to draw pictures, but I'll show you what we're doing. So the first 9 chapters, here's what we did. We had an object that traveled along a straight line and in 3 dimensions and all. But the thing was, see, every point, when this point traveled a certain distance and this point had a certain velocity, this point traveled the same distance, had the same velocity. So what we could do was treat this as a point object. Okay. Now let's say you're driving your car, and if the car is spinning and moving forward, then everything that you learned here does not apply here. Because then different points on the object will have different velocities and so on. Okay? So as soon as you add spin, things get complicated. Okay? But what we'll do is, so we'll consider the next simplest thing. We'll take an object, and this is the axis, and we'll make it rotate like that. So imagine a bicycle wheel, okay? A bicycle wheel, and here's the axis. You're holding onto the axle, and we'll rotate it like this. Okay? So now we'll consider this, except that now you can't treat this as a point object like this guy. Okay? And how did you describe the motion of this guy? Very good, my friend, very good. This was how you describe the motion, okay? Except that here, you see, this point is traveling at a different speed than this point, and so on. Okay? Now you have a problem. Is there anything that is the same for all the points? But that's one point. Is there something that's changing for all the points that is the same? So let me phrase it. Did you guys understand the question? Mm-hmm. So that's what we're looking for. Once I state the answer, it'll be so obvious. Okay? All right, so I'm going to give you the answer now. Okay? Now imagine the angle through which it rotates. Every point rotates through the same angle. Okay? And that's going to be the coordinate we use to describe its motion. Okay? So just like describing this motion involved giving that, what we'll do is, so now I'm going to draw another diagram. So here is the object. The axis is coming out of the plane of the sheet. Here is the x-axis. We're going to measure the angle with respect to the x-axis. Okay? So as this is the direction in which the wheel is rotating. And to describe this motion, what would involve in describing this motion? So let's say, okay, now I'm going to use this, and the recording people won't be able to see this, but here I have a bicycle wheel, and I'm going to, okay, do a motion. And here's a motion. How would you describe that motion? Yeah, so angular position, this theta as a function of time. Did you guys understand that? Okay. So as this object rotates, okay, we'll measure the angle with reference to some axis. Okay, so there's the x-axis. So looking at this way, we'll make it rotate like this. By convention, we take counterclockwise rotations as positive. Okay, and okay, so if this is marked over here, this is here. To what angle did that rotate? 90. 450. Okay, so you keep adding, you don't reset at 60, 360. All right, for now, the chapter says fixed axis, rigid body rotation. What does fixed axis mean?
The axis doesn't change.
The axis is not doing that. That's too complicated. Okay, so the axis is not precessing. Rigid body. What do we need that for?
Oh, it's not like bending, so
Right. Why do
the
we
form
need?
stays consistent.
Okay. Why are we saying rigid body?
So height stays the same?
No. Very good. Take a cup of coffee, stir the coffee. Different parts of the coffee are rotating to different degrees, different angles. Okay. Every part is rotating to the same angle. Okay. So we're keeping things simple. Okay. So that's what the rigid axis rotation is about. Okay. So fixed axis rotation of rigid objects. Okay. So that's what we're going to talk about. Okay. Now here's the deal. So everything you learned about motion in one dimension, okay? So this motion was described by that. Velocity was given by dx by dt. Acceleration was dv by dt, d square x by dt square. Okay. You'll have the exact same parallel. Okay. So you'll see exactly the same formula. So motion will be described by the angular position as a function of time. Okay. We'll define angular velocity, which will be what? D theta by dt. We'll define angular acceleration, which will be d square theta by dt square. Okay, and so on. And so we'll learn all this thing. So every formula that you've learned in the first 9 chapters, we'll relearn in this chapter. Okay, except that it will be applied to angular motion, rotational motion about fixed axis. Okay. All right, so every formula that you studied for one-dimensional motion, you'll study for fixed axis rotation. Okay, all right. So I will, as we see the new formula in this chapter, I'll remind you of what formula it corresponds to in 1D motion, okay? All right, so rotational variables, you already have learned that. It's the angular position that we'll use, okay? So angular quantities and so on. Right. Torques, you will learn, are the parallel of forces, okay? So now here's a device, so you can put an astronaut in there and make the spin very fast, and the astronaut can experience 20 g. You can subject them to 20 g accelerations. Yeah. So for instance, if you do the following, let's say, so here's the object and here's the room. So now what we'll do is we'll put an astronaut in here. So there's the head and there are the legs of the astronaut. And if you spin the astronaut, what happens? So if you subject the astronaut to 20 g acceleration, what would happen here? All the blood will go into their feet, and you can make them pass out. Okay. All right, so rotating objects, when an extended object rotates, all parts of the object do not have the same linear velocity. So when this is rotating, this guy is moving faster because he's got to cover a bigger circle than this guy. Okay, and so they don't all have the same linear velocity. Unlike when you're moving in a when you're driving in a car, every point in the car has the same velocity, and so you could treat that as a single point object, okay? All right, so hence the motion of the object cannot be analyzed treating it as a particle. However, for rigid objects, unlike for fluids, rotating about a fixed axis, all parts of the object rotate through the same angle, and that's what we needed. And we're going to use that coordinate to describe the motion of the object. Okay? So here's our object. Okay, this will be a reference line. So this is, that reference line is the parallel of what? That reference line is the parallel of the origin on your x coordinate. Okay, so all distances x was measured with reference to that origin. So our angular position will be measured with reference to that reference line. Okay? And so here's the angular position. So right now this object has been rotated through an angle theta with reference to. Okay, and by convention, counterclockwise rotations are taken to be positive, clockwise rotations are taken to be negative. Just like when you move to the right, that's positive and that's taken as negative distances. Okay, that's just convention. Just you can do this positive and that negative and nothing changes. Okay. Okay, so we'll define the angle as the arc length divided by the radius, okay, or the distance from the point of rotation, okay, the distance from the axis of rotation. So theta is S by R. And this, see, what are the dimensions of this guy? I'm sorry? Okay, so this is in meters, that's in meters. So it's dimensionless, okay? But we give it an artificial name, radians, okay? So 1 radian is when the arc length is R, okay? And 1 radian corresponds to roughly 57 degrees, okay? So theta is a dimensionless quantity and is given the artificial unit radians. Okay. All right, so we've said a lot, but let me back up. What we're studying is rotational motion of a rigid object about a fixed axis, okay? And so every point on the object is rotating through the same angle, and so that's the coordinate we are going to use to describe the motion. Okay, and what does describing motion mean? Giving theta as a function of time. Okay, and once you have a description of motion, once you have theta as a function of time, now you can calculate anything you want. You can calculate angular velocity, angular acceleration, and all that kind of stuff. Okay, so this is what we are looking for. Give me that. Okay, all right. You guys understanding this? All right. So first quantity we'll define as angular displacement. Okay, so let me show you the parallel of that. So in 1 dimension, okay, when you moved from x1 to x2, okay, so this was your position at time 2, this was your position at time 1. Your linear displacement was that, x2 minus x1, okay? So the parallel of that is angular displacement. So here was the object, so there was the disk, this was the initial position, and there is the final position, okay? And the angular displacement is that, okay? The difference in the two angles. So if it was initially at 30 degrees and finally went to 90 degrees, the angular displacement would be 60 degrees, okay? So 90 minus 30 degrees would be 60 degrees. Of course, we want to give that in radians. We'll be doing that in radians, and that will be pi by 3 radians. Okay. What if the angular displacement was minus pi by 3 radians? Which way did it rotate? Clockwise. Okay. All right. So if the displacement is plus 5 meters, it went to the right. And if the displacement is minus 5 meters, it went to the left, just like that. If the angular displacement is positive, it rotated counterclockwise, and if it's negative, then it rotated clockwise. Okay? You guys following this? It's 9 chapters coming at you fast in 1 hour. Okay? That's what's happening. All right, so angular, so average angular velocity, okay, we're saying angular speed, but okay, so right now, average linear velocity was defined as the displacement over time. And so this is the average angular velocity, which is displacement divided by time. Okay? So, and instantaneous angular velocity is, we're calling it speed because we haven't told you the direction yet, and we'll tell you the direction in 1 second. So instantaneous angular speed is denoted by omega. Okay, so this letter is omega. And that is d theta by dt. Okay? So let's do an example. Let's say, so, and this guy is the parallel of v is the parallel of dx by dt. Okay, so instant velocity is dx by dt, and angular velocity is d theta by dt. We'll tell you the direction in a second. Okay. All right. So let's do an example. Let's say theta t is given by 5t cubed plus 6t squared plus 4t plus 3. What is d theta by dt? The angular velocity as a function of time. Plus 4. Okay? So now you know how to do that. Okay? So here's the direction. So you use your right hand, okay? And if the object is rotating like that, you point your fingers in the direction of rotation and your thumb points in the direction of the velocity. Okay, so that's how you get the direction of the velocity. Okay? And now, so we are doing fixed axis rotation, so the velocity can either point that way or this way. Okay? And this is just like one-dimensional motion. You can either move to the right or to the left. Okay? So if you move to the right, we said that was 5 meters per second, and this was minus 3 meters per second. Okay? The sign told you the direction of the motion. Okay? Just like that, you can take this to be positive velocity and this to be negative velocity. Okay? So again, the direction of the velocity is found using point your fingers in the direction of the spin, your fingers in the direction of the spin, and your thumb is pointing in the direction of velocity. Okay? Everybody understand that? Okay. Question? Do you understand?
Oh, yeah, I'm just reading.
Okay. You understand?
Yeah, I didn't know how to write it. I said no.
Oh, no, just look at the picture. You don't have.
So,
Mm-hmm.
if it's moving clockwise, your thumb has to be pointing towards the object.
No, your thumb is always pointing in the direction of the axis. It's along the axis.
Okay.
Okay? So now there are two choices. Do you point this way or that way?
Yeah.
So your fingers point in the direction in which it's rotating, and your thumb points in that direction with your right hand. All right, so let's do it on the wheel here. Which way is the angular velocity pointing? No. It's pointing along the axis. It's always pointing along the axis. Okay? So it's pointing in that direction. Okay?
Okay.
Did you understand that?
Yeah.
Okay. Now, you're using your right hand, and the velocity is this way. Okay? You guys understand?
So if you look onto the front or on the right.
No, you're always using your right hand. Okay? All right. So So your velocity points along the axis. And which way along the axis is found out using your right hand, okay? So point your fingers in the direction of rotation, and your thumb points when you always use your right hand, okay? We could set up all these rules using your left hand, but everybody has to stick to the same rules, okay? I mean, we started calling this positive. There's nothing magical about that. You could call that direction as negative and this as positive. Everything would work fine. Okay, yep.
For you, you were turning it that way, and us, we are this way.
No, that's independent of which way you're. As long as you're looking at using your right hand.
But on your side, you're going the opposite way,
Oh, no, it's still.
because that's at my perspective, it's just.
Yeah. Well, now my hand is pointing this way, but even if I'm looking at it this from here, it's still the same direction. Yeah. Yeah, no, so it can be confusing. Ariel, you'll get it. We'll come, when we come to acceleration, it'll be fun. Okay? Karina's all confused because she missed out the first 5 minutes, which is the most important part of the lecture. All right. So we will be looking at motion where the direction of the angular velocity does not change. So this direction doesn't change, meaning the direction of the axis doesn't change. Okay, if the axis change, that motion becomes too complicated. Okay? And then you can't have just one angular function. You'd have to define three angles, and you would that motion will get a little too complex for us. When do you accelerate? When do you use the word acceleration? When the velocity changes. Okay? Okay, right now it's angular velocity. Okay? If the velocity changes, then you have angular acceleration. And angular acceleration is denoted by alpha. Okay? So in our example, okay, so let me go back and grab our example. Man, this is why I love the iPad. It's almost magical. It's not even funny, right? And now alpha t, okay, d omega by dt. You see, it's all contained in the formula. If the velocity does not change, alpha is 0. You don't have acceleration, okay? Only when omega angular velocity changes, that's when alpha is non-vanishing, okay? So it's all in the formula, and this is equal to 30t plus 12. Okay. Let's figure out the units. Okay. What are the units for this guy? Nothing. Radians. Okay. Radians, the artificial unit. What are the units for this guy? Radians per second. What are the units for this guy? Radians per second per second. Okay. Radians per second squared. All right. This was average angular acceleration, which was equal to change in angular velocity divided by change in over the time over which that change happened. And that is the parallel of, you saw this equation, average angular linear acceleration was v final minus v initial divided by t final minus t initial. Okay, so the parallel of that is that. Okay, and instantaneous angular acceleration is alpha is d omega by dt. Okay, so alpha, which was alpha t, which is d omega by dt, is the parallel of this. At acceleration as a function of time is dv by dt. That's what you saw for linear motion. And the parallel of that is alpha t is that. Okay. Okay. Every formula that you've seen in the first 9 chapters, we're getting a corresponding formula for angular motion. Okay. All right, now let's do the following. So let's go back to 1D motion. So here's the velocity. Here's the acceleration. What is happening to the speed? It's increasing, okay? So, very good. Okay, so velocity initial, velocity final. You saw that. What's happening to the speed? Decreasing, okay? Okay, so let's see this in our wheel, and I guess the reporting people will come to that in a second. Okay. So which direction is the velocity pointing on this wheel? This way. Which direction was the acceleration pointing? The speed was changing. That's right. Okay. Did you guys understand that? So when the speed decreased, the acceleration was pointing in the opposite direction as the velocity. Now they're pointing in the same direction. Okay. Did you guys understand that?
So giving a power.
Yeah, accelerating when speed is increasing, acceleration is pointing in the same direction as the velocity. Okay. And so it's the parallel of this. And so on the slides, okay. So what is happening? So this wheel was rotating that way in this direction. Velocity was pointing in this direction. And if the acceleration is pointing in the same direction, that means you're spinning it faster and faster. Okay? If the velocity was pointing that way, and if the acceleration is pointing in this direction, you're applying brakes. It's still spinning in that direction, except that it's slowing down. Okay? And what would the length of this vector mean? If the, I'm sorry? It's magnitude, but what does that mean? It's slowing down faster. Okay? Right. Okay. All right, so everybody understand this? Okay. And again, you're using your right hand to figure out the direction of the vectors. And the vector directions are always pointing in the direction of the axes. Okay? So this is the parallel of one-dimensional motion. Okay? So vectors can point, in 1D motion, vectors could point either to the right or to the left. And in rotational motion, they can only point along the axis, either that way or that way. Okay? You guys understanding this so far? Okay. How about you, my friend?
Yeah.
Good? All right. Okay, let me remind you of cross product. This we won't use these formula too much, but let's say you have a vector A and a vector B. Let's say these are in the XY plane. Anybody remember what direction A cross B is in? Yep, very good, very good. So what you do is you turn from A to B, and the direction in which the screw would move would be the direction of A cross B. So this would be the direction of A cross B. Okay? Or if you take your right hand, turn your fingers from A to B, your thumb points in the direction of A cross B. Okay? You move your fingers from A to B, your thumb points in the direction of A cross B. Okay? All right, so what diagram is showing you is the following. Okay, now this guy works only for small angles, so this should say d theta. Okay, so let's say you have an object, a disk that rotated through an angle, so it rotated through an angle d theta. The displacement is in that direction. D theta is a displacement. It's a displacement in that direction. And a point R from the axis moves a distance s. Okay, so this formula should be like that. Okay, the displacement of this point for an angular displacement d theta is d theta cross r, and so that's the vector in that direction, that's the vector in this direction, and this displacement will be perpendicular to this plane. Okay, so what this is saying is, I'll show you to you on the wheel. Okay, again, we won't be using these formulae too much, but I'll show it to you on the wheel. What that formula is talking about is the following. Okay. Okay, so here's this object. I'm going to rotate it through a small angle, d theta. Okay. So this displacement, d theta, is a vector in that direction. Remember, it rotated like that. That's the direction. Now the question is, how much did this point move? What was the displacement of that point? That point is r from the axis of rotation. Okay. D theta cross r is a vector in this direction. That's ds. Okay. That's what it was given. Okay. So again, for a small rotation, how much did this move? You understand, the further out you are, the greater the distance you move. This point moved only a small distance. This point moved a larger distance. Okay. So these diagrams from the book are not very good, but anyway, so that's what that is. Okay. So what this is saying is, so if this was a disk, when the disk rotated through a small angle, there is the angular displacement. The angular displacement is that, d theta. Okay, it's a vector pointing in that direction, and a point r, this point, which is r distance away from the axis of rotation, moves ds. That should be ds. Okay. I'm sorry? I'm sorry? Yeah, the small arc length. All right. Okay. It's tangent to that point, so it's approximately equal to the arc length. Yeah. It's going in a circular path, but its instantaneous displacement is in that direction. Yeah. All right, so what this formula is saying is, okay, again, if this is the disk and the disk is rotating this way, its angular velocity is pointing in that direction, and what is the direction of instantaneous velocity of this guy, this point? It's perpendicular to this r vector, okay? And it's omega cross r. So omega cross r gives you the instantaneous velocity of that, okay? It gives you the velocity of this guy, again. So when this thing is rotating instantaneously, each point, that point is, the velocity of that point is there. The velocity of this point is there, except that its speed is greater, okay? That's what it's giving you. Okay. This you have to understand. Okay, this T tells you tangential acceleration. Okay? The tangential acceleration, I don't know if you guys remember this from, velocity changing implies acceleration. When just the speed changes, so velocity can change by magnitude changing or direction changing. when speed changes is the magnitude change. That gives you tangential acceleration. What do we mean by tangential acceleration? It's tangent to the path. That's what that means. Okay? And when the direction changes, you get centripetal acceleration. Yeah. All right, let's do it over here. So let's say you're driving in a circular road and your speed is increasing as well. So you see the magnitude of the velocity is increasing and the direction is also increasing. Okay? So you have tangential acceleration. You have tangential acceleration. The tangential acceleration tells you how fast your speed is changing. And then you have centripetal acceleration. Why do you have this? I'm sorry? Exactly. Okay, so in this case, both your magnitude and direction is changing. So this guy accounts for this change in speed, change in magnitude. This guy accounts for change in direction. Okay? So if you were going around in a circular road at constant speed, what would this guy be? Zero. Very good. Who said that? Yeah. Good. Yep. All right, do you guys understand that? Okay. What if you were driving in a straight road? Which one would be zero? Very good. Very good. Right? All right. So, when a wheel is spinning, if you look at the velocity of any point on the wheel, and if it's spinning faster, if it has an angular acceleration, the speed of that point is changing and the direction is also changing. It has both tangential and centripetal acceleration. Okay? Those are my brakes. I could see that you like them. All right, so whenever you have angular acceleration, when this is non-zero, that means the wheel is spinning faster and faster, then you have tangential acceleration. Okay, so this guy should be tangential acceleration. So that's tangential acceleration. Okay. Again, we won't do these cross products too many times, but since you've already paid for it, I'm just introducing them. Okay? All right. Now we'll come to the formula that we will use. Okay. So what we're going to do is I'm going to okay. So here is the 1D motion. So let's say here is the x initial, x final, v initial, v final. This is A. And when A is constant, you had these formulae. Okay, so for constant A, you had V final was equal to V initial plus A times T. Okay, X final minus X initial was equal to V initial times T plus 1/2 A T square. Okay, and V final square was equal to V initial square plus 2A X final minus X initial. You guys remember these formulae? Okay. So we're going to do the exact same thing. So when was this true? When A was, very good, when acceleration was constant. So the parallel of linear acceleration is alpha. angular acceleration is constant. When angular acceleration is constant, we'll do the same formula. Omega final equal to omega initial plus alpha times t. Okay. Theta final minus theta initial equal to omega initial t plus 1/2 alpha t squared. Okay. Okay, help me out on this one. I get confused on this one.
WI
Omega I.
omega I squared
Very good.
plus 2
T,
alpha
Very good. Very good.
times theta
Final.
final minus theta initial.
Very good. All right, so these are called the kinematic equations, okay? And so we will, we won't derive them, we'll just tell them to you, okay? So when alpha is constant, what is this telling you? It's giving you angular velocity as a function of time. This is giving you angular position as a function of time, or angular displacement as a function of time if you want. And this is giving you angular velocity as a function of displacement, okay, as a function of position, angular position if you like, okay. So these guys work when alpha is constant, okay. So the rate at which the angular velocity is changing is constant, okay. All right, so for instance, I can illustrate this, okay. So again, the recording people will just have to imagine this. So, and here's constant angular acceleration, okay? Those guys, those formulas would apply. Did you guys understand that? Okay.
That would be in the other direction.
The acceleration was in the other direction, yeah. Was in the opposite direction of the velocity. All right. So I will just do one derivation because this is easy. All right, so we've already seen here, okay. So the angular acceleration was time derivative of angular velocity. Now what we want to do is derive formulas when this is constant, okay. And this is an equation, so what we'll do is we'll hit this guy with a hammer. There's the hammer, okay. So alpha is d omega by dt. What we'll do is we'll integrate both with respect to t from initial to final instant, t, dt. Okay. This guy was constant, so that guy just comes out. So alpha t initial to final. The left-hand side is t final minus t initial. And the right-hand side, okay, so you guys know from the fundamental theorem of calculus, okay, the integral undoes the derivative. It's omega t initial to final, which is omega t final minus omega t initial. Okay. And and now we'll call this t, so this is alpha times t equal to, we'll call that omega final minus omega initial. Okay? And omega final is omega initial plus alpha times t. Okay? So it's giving you your angular velocity as a function of time. Okay? So what this is saying is when alpha is constant, omega linearly changes with time. Is a linear function of time. Okay, that's what it's saying. Okay, so if alpha is positive, omega is increasing with time, and if alpha is negative, omega is decreasing with time. Okay. So these are called the kinematic equations. Okay. All right, so here's the angular displacement. What does it tell you? How, through what angle has the object rotated in this amount of time? Okay? When alpha is the acceleration. Okay, so if alpha were 0, this term would drop off, and the angle through which it's rotated is the angular velocity, which is constant times time. That's it. Okay, so if angular velocity was 10 radians per second, and in 5 seconds, how many radians has it rotated through? 50 radians, 10 times 5. Okay, that's what that formula says. You guys understanding this? I'm not going too fast, my friend?
Yeah, I think I get it.
Okay, a little fast?
Oh, a little bit.
Okay. One thing it takes time to is to get oriented. I mean, we were so used to talking about linear motion. Now we are showing you a totally different motion, a rotational motion, and that's equivalent to that linear motion. And that was one of the things about the seminars, isomorphic motion. They showed all different kinds of sets that were isomorphic to each other.
That was confusing.
It was. I mean, it's pure math talks are very hard to go to. Okay, but at least now you know what it is. I was at dinner with the speakers. The speaker, they don't go to all the math seminars because they don't understand other people's talks. You know, they stick to their own subgroups. So unless you're exposed to everything, how do you find what your niche is, right? That's what that's about. Yeah. All right. So this was linear motion, motion in one dimension. This is rotational motion about fixed axes. Okay. We're considering constant acceleration. Acceleration is constant. Okay, so these were the formula. This was final velocity as a function of time, final angular velocity as a function of time. This is position as a function of time, final angular position as a function of time. Okay. This was final angular velocity or speed squared as a function of displacement, final angular velocity as a function of displacement or as a function of position. Okay. And this was a final angular velocity. This is the average velocity. So here is the average velocity. Okay. All right, so now I'll give you the simple recipe. We've talked for over an hour now, and I probably have confused the heck out of you. But here's you replace x with theta, v with omega, and a with alpha. That's all. And you get everything that we've talked about so far. Okay. Now we'll give you a little more of the laundry list. Okay, that's coming in the next few pages. Okay. So what all did we have to replace? So we've done this. Okay, so we've done this replacement. Okay, well, we haven't told you what the replacement for mass is. That's a little complicated, and so we'll tell you it's moment of inertia. Okay, we haven't told you what is the replacement for force. The replacement for force is torque. Okay, what does F do to you? It gives you acceleration. Okay, that was Newton's second law. So that'll get replaced by, help me out, I forget. Torque I times alpha. Right? Okay. When is this the Newton's second law? Is this the correct form of Newton's second law?
Like in the X.
dP by dt. Okay, so when was this correct? When mass didn't change. Okay, just like that, you'll see how mass can change. I mean, moment of inertia can change. So we will introduce dL by dt. So here is the correct form of Newton's second law. Torque is the time rate of change of angular momentum. This L is angular momentum. This is linear momentum. Okay. This will reduce to that when I is constant. Okay. So this will reduce to that when I is constant. Okay. When is I not constant? So here's an ice skater. Okay. Spinning, and when they wrap their hands around, I has decreased. Okay, I is not constant. So when I is changing, you have to use this formula. Okay? Did you guys understand that? Okay, so now you have enough information to tell me this. What was the kinetic energy formula? 1/2 mv squared. So that was the kinetic energy of a car moving along a straight road. Okay? So now tell me the kinetic energy of a spinning wheel. What would be the formula be?
1/2 times inertia times.
Very good.
The angular velocity
St-
squared.
Omega square. Very good. Okay? So you just have to figure out a way to finding out the moment of inertia. Okay? And it turns out, okay, what is the mass of this guy? Whatever it is, the mass. In no circumstances does it change. The mass is fixed. The moment of inertia of a same object, it can have an infinite different values depending on how the mass is distributed. Okay? So for instance, if I'm spinning, my moment of inertia can have an infinite different values depending on what axis I'm spinning about. Okay, so now my moment of inertia is different and so on. Okay, so the moment of inertia of a same object can have infinitely different values, but the mass of an object is the same. Okay. All right, so we'll be building towards all of that. So what we've done is we learned these three replacement. X got replaced by theta, V got replaced by omega, A got replaced by alpha. So we'll learn the rest of these over this and the next chapter. Okay? All right. But now you're starting to get a sense for this. Okay? So this is still one-dimensional motion. It's one dimension because all the vectors point in the direction of the axes. Okay? Velocity vector points in the direction of axes. Acceleration points in the direction of the axis. The torques will point in the direction of the axis, and so on. Okay? All right. So what we're doing here is linear and angular speeds. What we're going to do is, so here's an object. There's the axis of rotation. The axis of rotation is coming out of the plane. It's rotating like that. And what you understand is you understand the following. The further you are from the axis of rotation, the faster you're going. So we're going to relate the linear speed of this point to the angular speed of this object. You all understand that. The faster you're rotating, the faster this thing is moving. Okay? And the further out you are, the faster you're moving. Okay? Okay, and that's what this is. So the linear speed of this point is r, the distance from the axis of rotation, times omega, the angular velocity. Okay. All right, so that's why you guys have seen some people put big wheels on their cars. Why do they put big wheels on the car?
To show off.
No.
Yeah.
Well, okay. That's part of the deal as well. But for the same angular velocity, your top speed will be greater. So if r is the radius of the wheel is bigger, and your engine gives you the same angular velocity, your linear speed will be higher. Okay, that's why they do it. So you increase the size of your wheel by 10%, your top speed will go up by 10%. Okay.
Similar for propellers?
I'm sorry?
Does it work similar for propellers or
No, well, yeah, okay, so it works in the sense that the way the propeller works is, okay, so here's a fan spinning. Let's say the fan is spinning this way, and depending on the orientation, it's pushing more wind in that direction, and your plane will move faster in this direction. So it's like a rocket. If you're burning more fuel and pushing it out, a rocket, if you spit out more fuel, your rate of acceleration is faster, and that's the same thing with the propeller. Higher burn rate corresponds to a bigger fan and a faster spin rate. Okay. Did that make sense? Okay. Are you a pilot? Are you a pilot?
No, understand that.
Okay. Are you a wannabe pilot?
Not really.
Not really, huh? I'm trying to get my son to learn gliding, but anyway. All right, so you guys understand? All right, so v is the linear speed of a point r distance from the axis. Omega is the angular velocity. All right, now if this guy, here's the axis of rotation, if this guy is accelerating, it has angular acceleration, then the speed is increasing, okay? And so you have tangential acceleration, and since the direction of the velocity is changing, you have radial acceleration or centripetal acceleration, okay? So when alpha is not zero, that is when you have angular acceleration, then tangential acceleration is not zero. You have tangential acceleration, okay? All right, that's what this formula tells you. The tangential acceleration, or the rate at which the speed of this thing is changing, is r times alpha. So if alpha were zero, this would be zero. Okay, so if alpha is zero, you have no tangential acceleration. You still have centripetal acceleration. Centripetal acceleration is your instantaneous speed squared divided by how far you are from the axis of rotation. Okay. So in going back to your propeller example, which we erased. Okay, so we'll do your propeller example. There's the propeller. The problem you face with the propeller, the faster you move, the tighter you have to hold on to this. If you move it too fast, the tip might fly off, break off and fly off. Okay. I don't know if that's a practical issue, but that's. Yeah. All right, so if you're rotating, if you have angular acceleration, then the speed of this point is increasing, and you have tangential acceleration. And since the direction of the velocity vector is changing, you have radial acceleration always. Okay, so when you have angular acceleration, then the acceleration of this point is in this direction because it has tangential acceleration and centripetal acceleration. If this were zero, if this guy were zero, this guy would be zero, and this would be pointing in that direction. Did you guys understand that? If this were zero, each point would only have radial acceleration if the object was rotating at constant angular velocity. All right. And it's in the formula. If alpha were zero, you have no tangential acceleration, and you still have centripetal acceleration. Okay? If your angular velocity is non-zero. All right. Now the next few slides are, now we are going to introduce the moment of inertia. The replacement for mass in rotational motion. Okay? All right, so here's how we'll do it. Okay, so here's an object that is spinning. Whenever you're moving, whenever anything moves, it has kinetic energy. Okay? You guys are calculus experts. Okay. you express everything in terms of what you've learned. Okay, so what is the kinetic energy of this car? Kinetic energy is 1/2 mv squared. Okay, so if you know the mass of an object and its velocity, you know its kinetic energy. Now the problem here is the following: when this thing is rotating, every little piece is moving with different velocity. So, well, you're not afraid of that. You just break this darn thing up into little pieces. Figure out the velocity of each one of them. Okay, and add them up. Okay, so there's the kinetic energy of each little piece, and then you sum it over all the pieces. And you've done plenty of series summations. You're good at it. Okay. All right. So here's the mass of each little piece. That's the velocity of each little piece. But the velocity of each little piece is related to something, the angular velocity. Vi is Ri omega. So here was the formula. V was R omega. It's how far you're from the axis of rotation times the angular velocity. Okay. So how far is this piece from the axis of rotation times the angular velocity? Now that is the same for all the pieces. So you're going to pull that out of the summation sign. Okay. So you see this is mi Ri square times omega square. So that's constant. That's the same for everything, and half is constant. And we'll call this the moment of inertia. So the moment of inertia is given by each mass times how far that piece is from the axis of rotation. Okay. Each piece times the distance squared. So you see, the further the mass is distributed from the axis of rotation, the greater its contribution to the moment of inertia. Okay? So if you're spinning, when your arms are far away, your arms are contributing more to your moment of inertia. When you bring them in, the contribution of your arms to the moment of inertia decreases. Okay? So that's how you can change your moment of inertia. Did you guys understand that? Okay. Okay, so the moment of inertia depends on how the mass is distributed about the axis of rotation. Okay. So now we'll show you for the same object, if you calculate the moment of inertia about this axis, this guy, the distance of this guy from the axis of rotation is 0, so this will not contribute. Only these two masses will contribute. And that is ma square plus ma square plus 0 for this guy plus 0 for that. So the moment of inertia of this object about that axis of rotation is 2ma squared. For the same object to rotate about that axis, okay? Now all four will contribute. This is ma square, that is ma square. This will contribute, mb square. Okay. Now the moment of inertia is increased by that much for the same object. And that's just 2 points. You could calculate the moment of inertia about this axis, about this axis, about that axis, about any axis you want. Okay, and it'll have different moment of inertias. Okay, so the same object can have an infinitely many number of moments of inertia. Now, generally in practice, you will probably only rotate it about that axis, or about this axis, or about this axis. Okay, so even though it can have infinitely many moments of inertia, you in practice will probably be interested in a finite number of moments of inertia. Okay. But did you guys understand the concept that the moment of inertia can be infinitely many? It's just a matter of how the mass is distributed about the axis of rotation. Okay. Okay, so the moment of inertia is an important enough concept where they give you tables. Okay, So for objects about various axes, they give you moments of inertia. Okay. Okay, but what it is so for a continuous object, if you wanted to calculate the moment of inertia about any axis, it turns out to be a triple integral. Okay, so this dm, okay, so let's say that's the density. Most of the case times you're considering a density that's not a function of x, y, and z, but dm would be density times the volume, dx, dy, dz. So it would be a triple, but most of the time you'd be considering, okay, so it would be this triple integral. And sometimes people are nice to you, so somebody has done these integrals for you. Okay, about special axes. So the moment of inertia of a hoop about that axis is just mr squared. The moment of inertia of a solid cylinder about that axis is mr squared by 2, and so on. The moment of inertia of a solid sphere, a bowling ball, is 2/5 mr squared. Okay. Of a thin spherical shell, that's a basketball, it's 2/3 mr squared. Okay, and so on. So they give you these moments of inertia. Okay. What is moment of inertia replacing? Mass. Very good. The moment of inertia in rotational motion plays the mass in linear motion. Okay? Okay, so this was linear motion, this was rotational motion. Okay. Okay, what this theorem helps you is the following. This is called the parallel axis theorem. Okay, so notice something about these guys. See, all these moments of inertia are given by an axis that passes through the center of mass of the object. Okay, so that's what these standard tables are about. Okay. What if you wanted, so here's the moment of inertia about the center of mass. What if you wanted to find the moment of inertia about an axis that's parallel to that, except that it doesn't pass through the center of mass? So then you use this theorem. Okay. And what this theorem tells you is the moment of inertia about that axis is the moment of inertia about the center of mass, which you can look it up on a table for a regular object, and then times m, mass of the object, times d squared. D is that distance. So now you have a way of calculating an infinitely many number of moments of inertia. Okay? And that's the parallel axis theorem. Okay. So this is d, and m is the mass of the object. Where do you find this? In a table. Okay. Now we'll talk about torques. Torque is denoted by tau. Okay. And torque is the replacement for the force, Okay. So when the mass didn't change, force gave you acceleration. Similarly, torques will give you angular acceleration. Okay. Okay, so that's what we're going to talk about. Okay, so here's an object, and it's fixed to rotate about that axis. Okay, so the axis is going into the board like that. And if you push at this point, this object will want to rotate counterclockwise. Now this guy, this push will want to make it rotate this way. So which way is it going to rotate? So let's say if you have an object like this, if I push in this direction and somebody else pushes in this direction, which way will it move?
So you-
Yeah, so whatever force wins out, that it moves in that direction. So similarly, it turns out that, okay, so let me ask you this. Let's say I apply a force like this, whose magnitude is equal to this magnitude. I'll apply 10 newtons in this direction, 10 newtons in this direction. Which way will it move? I'm sorry? Okay, what if this point was there? Hmm? Okay, so the magnitudes of the force are the same. This guy is not there. I just moved it further out. Will it still not rotate?
It would be the further one,
It'll rotate this way? Why?
because it's further.
Yeah, so not only does the force matter, it's how far from the axis of rotation matters. Okay, so this is called the moment arm. Okay, so it turns out that torque is equal to the magnitude of the force times the moment arm, or we'll call it R perpendicular. Okay, so not only does the torque matter, the torque will depend on the magnitude of the force applied and the moment arm. Okay, and the moment arm is the perpendicular distance from the line of action of the force. Okay, perpendicular distance from the axis of rotation. Okay. All right, what we're going to do is, so here's an object, here's the axis of rotation. Okay, so, and we're going to recruit Superman, and he's going to push this way. Is this object going to rotate? See, the moment arm of this guy is 0. Torque will be 0. Okay, and it won't rotate. And you can get a child to push in this direction, and the child will be able to rotate it. Okay, so this is Superman, this is child, and the child will beat Superman. Did you guys understand that? All right. So for the torque, it's the perpendicular distance, which is called the moment arm. So R perp. Okay, here R perp is 0. All right. The product of force, and moment arm is called the torque. Okay, so this is the force and this is the moment arm, and that's the torque. All right, so here we go. So in this simulation, okay, so here's the weight acting and there's the moment arm. It's this thing can rotate up on that axis, and here's the moment arm for this guy. This guy is rotating him clockwise about that point. This guy wants to rotate him counterclockwise, and since the torques are the same, it's balanced. Okay, now what we're going to do is move this guy over here. Now his moment arm decreased, so his torque decreased. This guy's torque, even though the force is the same, is greater because the moment arm is greater. And okay, all right. Okay, what will happen now? It will be stay balanced because this force is twice as big, but his moment is half as much as this guy. Okay, you guys understand? All right, so yeah. Oops, this. Okay. All right. So the product of the force and moment arm is called torque, okay? Now, so in this diagram, you apply a force. Now you understand why they put the knobs on the end. If they put it there, they've cut your moment arm into half, okay? And they'll give you more exercise. Your arms will get stronger, but you might also get madder, okay? All right. So here, between these two guys, the moment arms are the same, and since the magnitude is greater, this guy will have a greater torque than this guy. Here, the magnitudes are the same, the moment arm is smaller, this guy will have a smaller torque. Okay? And here, the magnitude is equal to that guy, okay? But his moment arm is only this much. So this guy will have a greater torque than that guy. Okay? So everybody understand that? All right. Okay, so now the vector notation in general, if the force is acting at an angle, the torque is calculated as the cross product. R is the vector from the point about which you're calculating the torque. F is the force. F is that force, and that's the point of application of the force. Okay, torque is R cross F. So this is the reason why you learned about cross products, okay, to calculate torques. One of the reasons why you can. Okay? And you saw that the cross product, this guy is perpendicular to the plane containing these two guys. So here's the plane containing these two, for this vector and that vector is that plane, and torque is perpendicular to that. Okay? And you saw that if the torque is in this direction, the angular acceleration will be in that direction, and it'll speed up in that direction. Okay? So this guy will rotate in that direction. Okay? Okay, so in this case, what it's doing is deriving the simple formula. I'm running out of time, so I'm not going to do any derivations. So this is a simple mass attached to a string, for instance, and it's rotating. And if you apply a force like that, its speed will change. It will get tangential acceleration. Okay, and so whenever it has tangential acceleration, it has angular acceleration. So the torque is force times the moment arm, which is mass. Force gives you tangential acceleration times that. Okay. Tangential acceleration. Okay, so I need to correct this form. So torque is tangential acceleration. Torque is force times the moment arm. The tangential acceleration force gives you tangential acceleration times r. Tangential acceleration is r times alpha. So this becomes mr squared times alpha. This guy is moment of inertia. Okay, so all it's doing is deriving Newton's second law. Torque is I times alpha, which is the parallel of F equal to ma. And hidden in all of this is, okay, when was this valid? When mass wasn't changing. When is this valid? When I does not change. Okay? So this is Newton's second law when I is constant. Okay? And we'll tell you the real form of the Newton's second law next chapter. This is the real form. Okay? And this will reduce to I alpha when I is constant. Okay. So here is the net torque is I times alpha. Okay, Newton's second law, which is the parallel of F equal to ma. Okay, I'm not going to derive this. What this is the following. So let's say you're going at a velocity v, and your engine is applying a force F like that. What is the rate at which your engine is working, or the power is the work times time, is force dotted with the velocity. Okay? And if they're in the same direction, it's F times V. So similarly, if a motor is rotating an engine, okay, and if there is friction, it has to apply a torque. Okay? So the rate at which that motor is working is the torque it is applied times the rotational speed of the engine. Okay, so that's the power of the motor. The torque it's applying times the angular velocity. Okay, you guys understand? Okay. So this is the parallel of that formula. Power was force times velocity. Power is force gets replaced by torque, and linear velocity got replaced by angular velocity. The work energy theorem was, so let's say for instance, here's an object. One person is applying a force like that, there's a friction force and all that. So the net work done on this guy, the work done by all the forces, shows up as change in kinetic energy. Similarly, so if you have an object, this guy is applying one torque, this guy is applying another torque. The work done by all these torques, the net work done, shows up as change in rotational kinetic energy. Okay. So when you're applying torques, you're increasing or decreasing rotational energy. When you're applying linear forces, these forces, when they're applied through the center of mass, all you're doing is changing linear kinetic energy. Okay? So these guys are not imparting rotational motion. All right, so now what all have you learned? So in the first part of this lecture, we saw this replacement. XVA got replaced by theta, omega, and alpha. Now you've seen the mass get replaced by moment of inertia, force get replaced by torque. Okay. See, to increase your knowledge of these two, you had to listen for another 40 minutes. That was the first hour for a replacement of these three, and the replacement of these two was another 40 minutes. Well, okay, you heard this as well. And for this guy, you have to wait till the next chapter. Okay, you guys see what's going on? But you already have an idea. Okay. All right, so this was a replacement for that. V was dx by dt, omega is d theta by dt. Okay. These formulae worked when A was constant. Here is those formulas when A was constant. F equal to ma, torque equal to I times alpha. Okay. The work done was integral under fx, so this guy work done was and in rotational motion that gets, we haven't derived this. Well, we haven't derived many things. That's the work done. Okay. If the torque changes with the angular position, that would be the work. Okay. Power is torque times omega, power is F times V. Okay. So this equation we'll learn in the next chapter. Angular momentum, linear momentum was mass times velocity. Angular momentum will be I times omega. Okay. All right, so I'll quickly go over this, a couple of slides, just fun stuff. I don't know, do any of you guys still use CDs? Have you ever seen CD? Have you ever used a CD?
Yeah.
Oh, you have, okay. All right. So here's the deal. On a CD, the information is packed in on these lines. Okay. For a CD track, that line is 5.4 kilometers. The length of that line is 5.4 kilometers. 5.4 kilometers is from here to US1. Okay? On a DVD, the same size disc, that line is 12 kilometers. So how did that get to be 12 kilometers? Well, the lines got closer and so on. Why did the lines get closer? We'll come to that in a second. For Blu-ray, that's 30 kilometers. That line has become from here to Palm Coast. Okay, so the information on that thing is packed as zeros and ones. If you went to the talk, you talked about Boolean algebra, okay? So this is 0, that is 1, 0, 1, and so on. Okay? And the way the line is read is you'll shine a laser, and when it hits that, you get a good reflection. And when you get a good reflection, that you're reading a flat spot. When you hit that, light gets scattered, you don't get a good reflection, and you know you hit a bump. Did you guys understand that? So that's how you're reading the information. All right, now what happens is the laser is standing there, and it just moves like that, okay? It'll move steadily like that, but the line has to go under the laser. When the laser is here, the line is traveling under the laser. Now this line has to travel at a constant rate. Okay, so the further out you are, the further out you are, omega has to increase because you want to keep the speed at which it goes under the laser the constant. You want to keep this constant, okay? So this should be VR omega. As R increases, omega has to decrease. So you have to have a variable speed motor. Did you guys understand that? So as the CD, you're starting to read from here, and as you're reading more and more, the rotational angular velocity of this disk is decreasing. Okay? So yeah, that's an engineering problem to solve. Okay? So you have to have variable speed motors to read these things. Now coming to the fact that how did the length increase? Okay, so the length increased because the groove spacing got smaller. What this spacing is that's the distance between these guys. Okay, now we'll come. How did the groove spacing decrease? Okay, well, manufacturing methods improved, but also here's the fact. Okay. So you're using a laser, this is the wavelength of the laser, okay? And if you use this wavelength, the smallest object you can read is this, the size of the wavelength. So now if you want to read a smaller object, what do you have to do? Very good. See, you got a college education, you're smart. And that's what this is. Blu-ray has a smaller wavelength than the red wavelength. So you get a smaller wavelength laser for cheap enough. You can pack more information.
Is that why they call it Blu-ray?
Yeah, that's why they call it Blu-ray. All right, so you see that? So this is 30 kilometers. From here to Palm Coast, from Blu-ray. And how much information have you packed? 25 gigabytes. Okay? So from here to Palm Coast, you are able to pack 25 gigabytes of information. Your DNA is 2 meters long. 2 meters is the width of this table. And you can pack 3 gigabytes of information. So for 25 gigabytes, 2 times 8, all you need is 15 meters. 15 meters instead of 30 kilometers. So the information density is 2,000 times greater in your DNA. All right. We have a ways to go to catch up to nature. All right. All right, guys.